So in number 60, we have a block released from rest at a height of 40 centimeters. It slides down a frictionless ramp and onto the first plateau, which has a length d, where the coefficient of friction is 0.5. If the block is still moving, it then slides down a second frictionless ramp through a height d over 2 and onto a lower plateau, which is length of d over 2, where the coefficient of friction is again 0.5. If the block is still moving, it then slides up a frictional ramp until it momentarily stops. The question is, where does the block stop? If the final position's on a plateau, state which one and give the distance L from the left side of that plateau. If the block reaches the ramp, give the height above the lower plateau where it momentarily stops. So, the reason this one's a little bit more interesting is we don't know where it's going to stop, and so we literally have to do this piece by piece. First thing I'm going to do, just put a couple of things here, and let's see if it makes it across the first plateau. To do that, I'm going to set h equals 0 at the height of the first plateau, and I'm trying to figure out what the velocity would be over here. And just using energy, starts out with gravitational potential energy. There's a force of friction, that should be an F sub k, sorry I typoed that one. Force of kinetic friction, times delta x times the cosine of the angle y, the force of friction is acting against the motion this way. So the angle between the displacement, that's going to be that, and the final is going to be kinetic energy. What's the force of friction? Well, force of gravity is going to be g times the mass. I'm just going to make the mass of this thing m. Just leave it a variable. So the force of gravity, 10m, normal force 10m, where 10 is the acceleration of gravity. And then the force of friction, remember, is just mu times the normal force. So in this case, that's going to be 5m. Plugging it into our equation then, force of friction becomes 5m. Mass times gravity times the height. Height is 0.4. Distance it's going to move for, the length of the ramp is also 0.4. Cosine of that is -1. Solving that, we can very quickly come up with 2m is equal to 1/2 mv squared. You can cancel the m's, multiply both sides by 2, and you'll discover, oh yeah, it is moving yet after the end of the first one. How fast? At 2 meters per second. Now, next step. We know it's going to gain more speed before it goes down to the second plateau. But now, what kind of energy does it have before it goes down that first hill? First thing I'm going to do is move h equals 0 down to here, just to keep things simple now. So now it starts out with gravitational potential and kinetic. And if we solve it then, we've got all of this. Remember, the initial velocity here is 2 meters per second. The height of this hill is 0.2. Force of kinetic friction, again, is 5m as before. The distance is going to slide across that plateau is 0.2, and cosine of this is this. If it doesn't make it across the plateau, we'll end up with the initial energy plus the work is going to be negative. It's not going to have enough or any kinetic energy by the time it gets to the other side. But if we solve this one real quick, we'll discover that, oh, yeah, it still has a velocity here at the bottom of this point right here. It is still moving with a velocity of √6 meters per second. Final step on this one, we're trying to figure out how far up the ramp it's going to go before it briefly stops. How are we going to do that? Well, we're going to measure the height that it goes to. If we do this, I'm going to change this real quick to capital H over here. And we're going to figure out the maximum height above the bottom here that this is going to go. So this becomes capital H over here. Velocity squared becomes 6. Remember, our velocity at the end there was square root of 6. If we solve this, then we get 3 equals 10h after we divide m on both sides. And we discover that h is 0.3 meters. Please note that this m here is not the variable m I was using for the mass of this. This literally is meters. We can solve this without knowing the mass of the thing. All right, good luck on this one. I realize it was just painful. Have a good night.